Let's go ahead and work some examples of finding these double integrals over these more general regions. Part of the fun of these examples will be getting used to what type of region we're dealing with, but I'll kind of walk us through some of that when we get to ones where we have to worry about that. For this first example, though, the instructions kind of already tell us that we can do it either way. So they want us to do both orders, and we can't do that unless we do have a region that is type 1 and type 2. So the region that they tell us that we have here will be both types, and we want to actually set this up in both ways. So we're looking for this double integral. They tell us D, and they give a description of how we set that up. But let's actually draw this out. In fact, for most of these problems, in fact, probably all of these problems, we want to first draw this thing to get an idea of what we're even talking about. So we'll keep in mind we have y equals x, y equals 4, and x equals 0. We'll go ahead and actually draw those in here. We have y equals x, y equals 4, and x equals 0. X equals 0 is just the y-axis, so it doesn't really show up too well there, but we just remember it's the y-axis. And we're working with this triangle. Our region is just a triangle. We might even maybe shade that in using integral. Actually, let's just do f and g from 0 to, hopefully it's pretty obvious that this point over here is 4, 4. So our x's are going from 0 to 4. That's the easiest way I know to shade inner regions, though we might not always do that. But the point here is I want to make it really clear that we are working with this triangle and we're trying to integrate over it. If we want to set this up as a type 1 region, keep in mind there we're looking at cross sections where we keep x constant. We're going between two functions. Y equals a function of x, so we're going from the bottom here is just y equals x. The top here is y equals 4. Those are the two functions that we're dealing with. The x values we need to keep in mind are going from 0 to 4. You might, if we're more complicated one, you might actually have to solve for what this intersection point is. But of course, if y equals x and y equals 4, then x has to be 4 as well. So as a type 1, like I said, our x is going from 0 to 4. Our y's are going from the bottom is x and the top was 4. Our function, in fact, our function is just whatever it was right here. That's not affected by any of our setting up of D as type 1 or type 2. And then we have to keep in mind what order we're doing this in. When it's a type 1, it's going to be dy dx. Because we're integrating with x constant with respect to y, and then we're integrating over those x's. If we're doing it as type 2 instead, going back to our picture, this time we're looking at cross sections where we're keeping y constant. So here, you can think of these as the bottom function or top function, or you can think of the left to right function. So the rightmost one is 0. Or sorry, the leftmost one is 0. The rightmost one is this, and we want to think about this in terms of functions of x in terms of y. So our formula of y equals x will become x equals y. So we're going from 0 to x. From 0 to y. Of course, our y values are going from 0 to 4, and those are going to be our outside limits. So this time our integral is 0 to 4, 0 to y of the same function. And regardless of which one we do, these should give us the same answer at the end. Now, one of these actually turns out to be a lot easier than the other one. If we were to try to integrate are, if we're trying to do the type 1 version first, we have, well, we're dealing with a dy, so we're integrating with respect to y. We have y squared times an exponential with y in it. That would require actually 2 integration by parts to do. And we also even have to deal with the x giving us extra factors out in front. This would be kind of a pain to do. Not impossible, but it would be fairly painful. The type 2 is actually a lot easier. And this is kind of similar to a problem that we did in the last section, where the exponential times something outside is a little bit messier when we're doing the integration by parts version of it. But actually the type 2 here is a lot easier. So let's do that one. So we're integrating this with respect to x. The y squared just kind of sits there. The e to the xy, we need to integrate that. So the y squared, what is the integral of e to the xy? Well, we have when we integrate e to some constant times x, we end up with e to that same constant times x, but then we have to divide by that, whatever that constant was. So this time we actually end up dividing by y. And keep in mind we do have our limits still from 0 to y. We'll go ahead and simplify this, so we just have a y out in front. Now we get to plug in our functions. So one of the functions is a constant, but the other function is not. We still go through the same process that we're used to. We plug in the top function. We subtract what we get when we plug in the bottom function. So we'll have a y e to the y times y, because we're replacing x with the y. So we have y squared minus y times e to the 0. Well, e to the 0 is 1, so we just have a y. And now we're integrating y times e to the y squared minus y. Now you might be thinking, well, don't we have to use an integration by parts here? Because we have y times an exponential. But the fact is that we have a y squared here. What we're going to do to deal with that is make a substitution. We're going to let u equal y squared, which means that du is going to be 2y dy. This y dy is exactly what we need to deal with here. And we end up just having to deal with an extra 1/2 in our formula. In fact, if you go through all the work of this, this turns into a 1/2 e to the y squared. Of course, the y that we have here just turns into 1/2 y squared. We're going to take that from 0 to 4. When we plug those in, we'll have a 1/2 e to the 16, because we're plugging in 4. We'll have a minus 8 from plugging in 4, but we'll also get a minus 1/2, because when we plug in 0 into the e to the y squared, plugging 0 in here just gives us 0. And so those constants will actually combine to give us a minus 17/2. I'll leave you to maybe fill in the details if you need to. But the point here is that we are able to do this integration, even though we had functions in our limits. We just treated them like we would normally with a constant, and then we had to do whatever substitutions that we normally would have had to do for Calc 1 or Calc 2. Let's move on to problem 19, which is actually going to be fairly similar to what we just did. They already tell us that we are going to be working with a triangular region, but they only give us the vertices this time. They didn't give it to us as lines. They want us to integrate y squared, so at least this is a simpler integrand. But the very first thing we want to do is actually draw the region, because we need to determine what type of region we're working with. They're not guaranteeing here that we have a type 1 or type 2. We don't know what it is yet. So let's draw this region. Of course, they told us the vertices. We have the point 0, 1, we have 1, 2, and we have 4, 1. So we have those points there. I'll go ahead and connect them with segments. And I think it's thinking I'm double clicking, and so it's actually changing it from segment to cursor. And let's actually, I don't know why it made those so big. Let's just make them down to 3 and just make everything black. So this is our region. We're wanting to integrate y squared over this triangle. Now, is this a type 1 or a type 2? Well, to be a type 1, remember we're looking at cross sections where we keep x constant. So if I go ahead and maybe, so go ahead and make a slider here, going between for our x value is going from 0 to 4. We're going to look at the lines that x equals a, as a varies from 0 to 4. And if we look at these cross sections, do we always have a function on as our top boundary and a function for our bottom boundary? Well, our bottom boundary is always just y equals 1. We just had that horizontal line. So that actually wouldn't be too bad. But our top boundary, it switches when we get to x equals 1. At the point 1, 2, it switches between having this line here to having that line there. Those are two different functions. Now, it wouldn't be impossible to split this up into two regions. If we go ahead and plot the point, say 1, 1, and make the segment from that vertex down to D. And let's turn off the labels here. Thank you. There we go. If we were to draw that line segment there, we could split it up into two type 1 regions. So for this first type 1 region, we'd have y equals 1 to whatever this line is here. I think that'd be y equals x plus 1. Over here, we'd go from y equals 1 to whatever line that one is. That one might be a little bit more work to actually find, so we'll leave that for now. But the point here is the whole thing is not a type 1 region, because we're not working with a single function on top. Unless you want to consider this piecewise function. But then you're even trying to... It just gets a little bit messy. It's not the easiest way to deal with it. Instead, what we might want to do is go ahead and take these out of there. And look at cross sections where we keep y constant. So our y values are going from 1 to 2. We're going to go ahead and put it in the lines y equals b. So as we vary b, as we vary these horizontal lines, the horizontal lines are only hitting you could say a bottom function or a leftmost function of this line over here, and then a topmost or rightmost function of this line over here. The third line segment of our triangle just turns out to actually be one of our cross sections by itself. So this actually turns out to be a very nice type 2 region, where we have to deal with what are these line segments. So I'll leave it up to you to determine what those line segments are. That's just an algebra problem. But one of them is, we actually mentioned here, is y equals x plus 1. which, since we're going to do as a type 2 region, we want to actually solve for x, so x equals y minus 1. The other line, if you actually put that as a function x of y, would be x equals 7 minus 3y. So I'll leave it to you to actually show that for yourself. Of course, we do need to determine what are going to be the limits of our y, but we've already actually done that. When I defined b, I noted that y is going from 1 to 2. So this integral, the double integral over d of y squared, we're going to integrate y from 1 to 2, integrate the x values, then from y minus 1, because that is the rightmost one, and then 7 minus 3y is our, leftmost to rightmost. We're integrating y squared, dx, dy. And then from this point on, the setup is already done. We just kind of crank through the integration, how we would do integration before, just remembering to plug in functions when we get to them. The first step is actually pretty nice because there's no x's. We end up just getting to turn this into x times y squared. Keep in mind we are plugging in these values for x. So we end up with 7 minus 3y times y squared minus y minus 1 times y squared. Before we integrate with respect to y, let's go ahead and actually combine like terms. It actually turns out we get 8y squared minus 4y cubed. When we integrate that, we get 8 thirds y cubed minus y to the 4th. We evaluate that from 1 to 2, which gives us a 64 thirds, because 8 times 2 cubed is another 8, so 64 minus 2 to the 4th power is 16. When we plug in 1, we have 8 thirds minus 1. And then we work all this out, and assuming I did it all right, that should come out to be 11 thirds. So as you can kind of tell here, a lot of the issue is going to be the setup. Can we get this? Can we figure out what we're going to be doing with our region? How do we set that up in terms of type 1 or type 2? And once we get the integral, it's kind of almost straightforward, assuming that the actual integration step isn't too nasty. Let's take a look at problem 21. Here we have it's just find a double integral over a region. They gave us a description of the region. D here is, well, it says region that's bounded by the circle with center the origin or radius 2. We could say that's a disk, is the term that we're using here, and we know how to graph that. So x squared plus y squared equals 4. We have to square that 2 to get 4. And we're just looking at the inside of this disk. And we want to look at what's the integral of 2x minus y over this region. Now, we actually could do this as a type 1 or a type 2. Remember, if we're looking at just horizontal and vertical lines, let's go ahead and even put those in here. So our x values can go from -2 to 2. If we look at x equals a, no matter where we put our vertical line, we're not hitting that boundary more than twice. We have a top function and a bottom function. In fact, we could look at y equals a as well. I don't have to change the limits there. There's still -2 to 2. we have exactly the same thing there. There is a leftmost function and a rightmost function. Unfortunately here, what those actual functions are is kind of annoying. So we have to take our x squared plus y squared equals 4 and solve that. Let's say solve that for y. We have y squared equals 4 minus x squared. And then we take the square root, and we have plus or minus the square root of 4 minus x squared. So you could say in this case, this is what we'd be doing for type 1, where we've expressed y as a function of x, but then we have two functions. Our top function is the square root of 4 minus x squared. Our bottom function is negative square root of 4 minus x squared. As a type 2, we do the same thing, except we'd solve for x. We still have a square root where we have a plus or minus in front of it. And so either way, we're going to have this square root as our boundary functions. Since we can go ahead and actually do either one, I'm going to go ahead and do the type 1 route using the function that I've already solved for here. In some cases, again, it could be easier to do one or the other. Actually, that might depend on what the integrand is here, whether it be easier to integrate with respect to x first versus y. But in this particular case, it won't really matter. These are both being treated kind of equally. They're both linear terms. So I'm just going to go ahead and do it as a type 1. So again, we already mentioned here that the x values are going to go from -2 to 2. Our y values are going to go between these two possible functions. So from negative square root of 4 minus x squared to the square root of 4 minus x squared. We still have our function in there. We're integrating with respect to y first, and then x. And it looks really complicated, doesn't it? When we have complicated functions here, it can actually look very intimidating. But it's not really too bad. So again, we first integrate 2x minus y with respect to y. That means we get a 2xy minus 1/2 y squared. We're evaluating that from negative square root of 4 minus x squared to 4 minus x squared. That means we go ahead and plug these into our y values. So first we plug in the top square root into both of those. So we'll have a 2x square root of 4 minus x squared minus 1/2 of that thing squared. Well, that thing squared is just 4 minus x squared. Then we subtract what we get when we plug in negative square root of 4 minus x squared. And really, it's going to be exactly the same kind of thing, except the y here, the negative doesn't go away, so we end up just getting a minus. We have a negative 2x square root of 4 minus x squared minus 1/2 4 minus x squared. And let's see if anything cancels out or combines. Well, maybe not exactly what you'd want to have happen. What actually cancels out is the negative 1/2 4 minus x squared minus itself. So that all the signs work out so that those actually cancel each other out. The parts with the square root of them actually combine because these two negatives end up making this plus itself. So we end up getting the integral from -2 to 2 of 4x square root of 4 minus x squared. But at least it doesn't look quite as bad, even if it does have a square root in it. And it actually turns out very nice, because what we have here is a substitution. We can set u equal 4 minus x squared. That means that du is equal to, well, it's not 4x, but it's a negative 2x dx. We have a 2 from our 4 times x dx. So we end up getting a negative 2 over here. So negative 2, integral, we'll deal with the limits in a second. But then we have the square root of u du. Our limits, when we go ahead and put in negative 2 and 2 in for x, what do we get? Well, it turns out in both cases we get 0, which is kind of interesting. We're integrating from 0 to 0. And that can only happen if we have 0 overall. So this is a case where things actually worked out very weirdly at the very end, where we had we're going from 0 to 0 and we end up with 0. Does that make any sense? Well, let's actually go ahead and graph this thing. So if we go ahead and put in the three-dimensional stuff, so you can go ahead and move this down here. So we have our circle that we're integrating over, and our function, remember our function, f of xy is equal to 2x minus y. And why did you not put that in there? There we go. So z equals 2x minus y is a plane. It cuts through our circle, and if you look at the part that's inside that circle, half of it is below the x-axis or the xy plane. Half of it is above the xy plane. And that's not, I'm not saying half there as a very vague kind of half and half kind of thing. I'm saying it literally is, this plane literally cuts that circle into two pieces. On this piece over here, it's below, and on this piece over here, it's above. And so if we look at the volume, so if we look at the positive volume under that plane over here, and the negative volume above this plane over here, those are actually equal to each other. At least in absolute value. One's positive, one's negative. But if we add them together, they completely cancel each other out. And so even though we went through this weirdness of using this fact that we're going from the number to itself, it really does work out correctly. If this last step doesn't satisfy you, maybe you don't want to change from negative 2 to 2 and end up going back to x's afterwards and see that the same thing everything will cancel itself out. Let's do one more problem in this video. So here we're looking at problem 23. They're asking us to find the volume of a given solid. So this time they're not just telling us to do a double integral, but they're asking us to find a volume, and we're going to be using a double integral to make that happen. But we're working with this plane, and we're looking at a region enclosed by two parabolas, y equals x squared and x equals y squared. If we actually go ahead and graph those, so let's go ahead and let's actually graph them all as surfaces. So we have y equals x squared, and it did not do that as a surface. Second. Sometimes GeoGebra can be a little finicky about whether or not it's going to turn something into a cylinder, or if it's just going to graph it as a function in the xy plane. So y equals x squared turns into this parabolic cylinder. X equals y squared does the same. We actually have two cylinders here, and the intersection, or the part that's contained between them, is kind of in this little sliver here. Everything that's in there, everything that's not between them is in some unbounded region out there. We want to look at the plane. This plane is given by 3x plus 2y minus z is equal to 0. So we've got this plane that cuts through here, and we want to look at everything that's below that plane, meaning that we want to basically bound the bottom of it by z equals 0. So we have this region that's underneath this plane, above the xy plane, but in between those two parabolic cylinders. Might be a little hard to see exactly what's being contained in there, but it's a little piece that's in there. Now, really what we want to be dealing with is looking at the actual region. So we already know that we're looking at the volume underneath a particular function, and so all we're really going to be doing is taking the double integral of that function over the region that we're going to be dealing with, and that region is going to be defined using that y equals x squared and x equals y squared. So let's actually look at the region itself. So our region is y equals x squared and x equals y squared. So we have this little piece in here that we want to integrate over. Now we could view this either as a type 1 or a type 2. If we want to view it as a type 1, we have a topmost function here of, well, this is given as y equals x squared, or sorry, this curve here is given as x equals y squared. We have to solve that for y, and so we treat that as y equals square root of x. So our topmost function would be y equals square root of x. Our bottommost would be y equals x squared. But we have it nicely defined there for a type 1 function. If we want to do it as type 2 instead, now our leftmost function, this is still the x equals y squared, but now we do want to keep it that way and have it as x equals y squared. Now the rightmost function, this one needs to be changed from y equals x squared to x equals square root of y. Again, it doesn't really matter which one we choose. I'm going to go ahead and do this as a type 1. I'm just basically going to default to type 1 because it's a little easier for us to think as y equals a function of x. So I'm going to say my D is going to be the region where the x values are going to go from 0 to 1. And we had to get that information from our graph here. This point here where they intersect is the point 1, 1. That's where x squared equals square root of x. And then our y value is going from x squared to square root of x. That's our region as a type 1. So our volume, the double integral over this d of this, well, we have to turn this into a function. We're saying that z equals x squared, or not x squared, z equals 3x plus 2y. We're going to use the information that we got about d. This we're going from 0 to 1, then x squared to square root of x. We have 3x plus 2y. We're integrating with respect to y first and then x. And now it is straightforward. We just go through all the motion of integration. The integral of 3x plus 2y with respect to y, well, 3x becomes 3xy. 2y becomes y squared. We saw the limits that we already had. We go ahead and plug those limits in. So this is, we have 3x times square root of x. Then we have square root of x squared is just x. We're subtracting what we get when we plug in x squared. So 3x times x squared is 3x cubed. Then we have x squared squared is x to the 4th. And I'm even going to go ahead and write this all out. So we have 3x, and this is x times square root of x. This is x times x to the 1/2. And adding those powers together, x to the 1, x to the 1/2, we have x to the 3/2. We saw the x that's right here. Then this minus sign gets distributed. We do integration. It's just a normal integral problem now. So this one is going to be x to the 5 halves because we add 1 to that power, but then we end up dividing by the new power. So 3 divided by 5 halves is actually 6/5. The x here becomes a 1/2 x squared. The minus 3x to the third is going to be a negative 3/4 x to the fourth. And then finally, the minus x to the fourth becomes minus 1/5 x to the fifth. We're going from 0 to 1. Of course, plugging in 0 is just going to give us 0. So that part we don't really need to worry about. Really, we're just going to be plugging in 1. We get 6/5 plus 1/2 minus 3/4 minus 1/5. When we go ahead and put those together, in fact, the 6/5 and the minus 1/5 combine very nicely to give us a 1. 1 plus 1/2 minus 3/4 end up giving us a 3/4. Alright, so I definitely want to go through some more problems, but I don't want to put everything all in one video. I'm going to go ahead and do 3 more problems in the next video. And we'll kind of get into some of the importance of being able to do these multiple ways, having a type 1 or a type 2 region. But I'll leave those for now. So I'll see you then.